A very good afternoon, everyone. This is Arun Sharma from MIDASoft, and today I'll be presenting the session 8 of our Midas Elite Center course. The topic for the course is Numerical Analysis Modeling Demonstration for Fundamental Finite Element Analysis Concepts. Midas holds the copyright for the materials of the presentation that is being shared, so please do not share it without our permission to any third party. At the end of this course, participant will be able to understand the modeling concepts, which will cover how to determine the size and element types, boundary and loading conditions, different analysis method, how to determine various analysis type based on the project needs, then interpolation of the results, so basically determining deformations, stresses of ground, as well as forces and stresses in structural elements. This session is divided into 4 chapters, and between chapters 1 and 2, 2 and 3, 3 and 4, we'll have 3 quizzes. In these quizzes, as you have seen so far, there will be a 5-minute quiz with 3 questions. And in the first chapter, we'll be talking about the background of finite element method of analysis. In chapter 2, we'll be going over how to set up the analysis model. Then chapter 3, we'll be talking about the analysis types and how to perform them. And in the end, we'll be taking up a case study where we'll be going over the key points that we learned today with an example. So let's start chapter 1, background of finite element method. In this chapter, we'll be covering the history of finite element analysis, how it was originated, how it and what all transformations it has gone through, and what are the main principle of this type of analysis. So finite element method, while it is difficult to quote a date of invention of the finite element method, the method was first originated from a need to solve complex elasticity and structural analysis problems in civil and aeronautical engineering. Its development can be tracked back to the work of A. Rennikov and R. Courant, and then later in China in 1960s, based on the computation of dam construction, K. Feng proposed a systematic numerical method for solving partial differential equations, and the method was called finite difference method based on variation principle. This is an independent type of analysis to finite element method. Although these pioneers had different theories for finite element method analysis, but there was one essential characteristic that was common in all, which was mesh discretization of a continuous domain into a set of discrete subdomains, usually called elements. So at the background of finite element method lies a common principle which is called mesh discretization, which means you have to divide a bigger object into finer into subdomains, and then subdomains could be treated as a group of finite elements that can be used to replicate the behavior of the structure and study the stress propagation through the system. So basically, Rennikov's work discretizes the domain by using a lattice analogy, while Courant's approach divides the domain into finite triangular subregions to solve second-order elliptical partial differential equations, which are also known as PDEs, that arises from the problem of torsion of a cylinder. So these, like I said, these pioneers had different ways to approach the problem, but at the very base they were dealing with the discretization of domains. Then this method obtained its real impetus in 1960s and 1970s by the development of J.H. Argyes and co-workers at the University of Stuttgart, R.W. Claw and his co-workers at UC Berkeley, then O.C. Zinkwit and co-workers in the University of Swansea, and Richard Galler and co-workers at Cornell University. So these are all pioneer in these in the industry of numerical modeling. They worked in different countries in same time, and came up with the different approaches for finite element method. Further impetus was provided in these years by available open source finite element software programs. So this was the era when the first software came out for handling finite element analysis, and NASA sponsored the original version of the software called Nastran. And a rigorous mathematical basis was provided in 1973 with the publication by Strang and Fix. The method has since been generalized for numerical modeling in a wide variety of engineering disciplines, for example, electromagnetism, heat transfer, and fluid dynamics. So basically, based on these this publication, it led to several, I should not say several, basically a common platform or common or generalized process was set up in place to simulate various numerical modeling studies to come up with the different types of analogies and models and different software to run these kinds of analysis, because these PDEs or partial differential equations of high order get increasingly difficult when you go into the complexities of different material behavior and their interaction with the external environment. So that is the history of finite element analysis, and this is something it's good to know but not directly applicable to our routine work. So let's move on to the principles of finite element method. For this, it is very essential that you understand what is the basic procedure or the background of, or sorry, not the background, but the backbone of finite element method. So there are 5 essential steps in finite element method. First is the discretization, then defining internal conditions, then applying the external conditions, then performing the analysis, and then finally the result extraction. I'll go over each and every topic in detail in the following slides, starting with discretization. So as you can see here, this is a real project site. So when engineers start working, they have to look at the project site, they have to read through the maps and create geometry. For creating geometry, there are several tools available. You can work on AutoCAD, you can work with MicroStation, you can work with SolidWorks. So depending upon what tool you use for generating different types of geometries and tools, you can generate these geometry. Now once this geometry is generated, you have to divide them into different layers using solids, and once you have this solid geometry ready, then you have to divide these solids into finer elements called finite element, and this process of dividing the solid into a finer mesh is called discretization. So this is the key ingredient for your finite element analysis approach. Then comes the internal condition, which is primarily called applying a constitutive material model. So let's recap what is the complete flow of the process. So when you are defining the constitutive material model, you have to basically apply the material properties and define the equilibrium conditions that are used for stiffness relations. And when these ingredients are placed in this in composition, then structure stiffness matrix is developed using the element stiffness matrices. So what does that mean is, let's say you have done the discretization. Now you have to identify what are the different layers made of, and to these different layers you have to apply the constitutive material model, which will go in and form the stiffness matrix. So the stiffness matrix is formed based on the element size and the behavior that you have assigned in there. So what happens is that a system of equations is then constructed for the entire structure. So going back to the basics, as you know, force is equal to K times U, where force is the loads, K is the stiffness matrix, and U is the displacement. So you can see in this equation right now what we are doing is we are entering the value for K. So when you give the program the constitutive material models, you are basically telling them the program the material properties and the elements in that which will form the stiffness matrix. So right now we have provided the program or the software, or in our computations we have provided the value of this stiffness matrix. Then the third step is called external condition, and the reason it's called external condition is that these are not controlled by the structure internally. These are the variables or parameters outside the structure. So this is something that is imposed onto your model. So in order to solve the equations for the whole structure, the boundary conditions are enforced, and displacements and or rotations at each unconstrained node are calculated under applied loads or prescribed displacement. So what does that mean? So let's say this is your model, and you have done the discretization, you have applied the material properties, so you have given the internal conditions as how the structure will behave internally, how will the stresses propagate. But right now this is not a stable structure because it doesn't know as how it is constrained um, uh, in the vicinity. So the structure can go any direction from here. It can go vertically down infinitely, it can go vertically up, right, left, back, forward. So what you have to do is apply boundary conditions all around the periphery of your models. Once you have applied the boundary conditions, then you apply the external loads, which is like a vertical load and horizontal load. So this is a model of a let's say a dam, and you can have void sulfate and so let's say some external vertical loads on top, and then the horizontal pressure due to water or due to other types of lateral loads can be applied. So these are the external conditions. So therefore boundary conditions and load conditions form the external conditions. So let's look at that formula again. So in this F is equal to K times U, we are now applying the F, which is the forces that are known in this equation. So we are done with the component K, and now we have applied F. Then we have to move on and perform the analysis to solve the equations. So finite element method is found very helpful for the following types of analysis, such as deep foundations, where you definitely need soil structure interaction, then deep excavations, where you need to analyze the forces in temporary structures, then unconventional tunnel intersections, where you have to see the stresses as well as displacement in the connecting galleries or the connecting points or the junction points, then shield tunnel boring machine analysis for considering excavation sequences, vibration analysis for earthquake and blasting situations, slope stability analysis, consolidation analysis, groundwater flow. So all these types of day-to-day geotechnical problems or analysis require finite element modeling and analysis. So if we look at the formula again, what we are doing under analysis is that our, as a geotechnical engineer, our prime concern is to find this U, which is the displacement. So what program does is it uses this mathematical matrix inversion method, where it determines U by inverse of the stiffness matrix times the loads. So this matrix is known, load is known, we can find the displacement. So when you are running the analysis, actually the program is performing this computation to get you the displacements. So after performing the analysis, here it's time to look at the results. So the results can be obtained in contour plots, as you can see here, can be obtained as structural force diagrams. This is a diagram of an anchor bolt or a soil nail to stabilize this MSE wall, or the results can be obtained in a tabular format. So depending upon uh, different types of results, it becomes easier for engineers to interpret the result in different formats, and that's why for any uh, tool that you use, it should be flexible enough to suggest or provide you results in different layouts and formats. So if we look at that equation for one last time, you can see in this step we have actually determined U, which is the displacement or the final result that we needed. So let's go over the points that we learned in this particular chapter. So the approaches used by pioneers are different, but they share one essential characteristic, which is mesh discretization of continuous domain into a set of discrete subdomains, usually called elements. Procedure of finite element method includes 5 main steps in the given order. First, discretization, then internal condition, where you apply constitutive material models, then external condition, where you apply boundaries and loads, then analysis and result. Discretization means breaking down the geometry into finite elements. It's also known as meshing in our day-to-day language. Internal condition involves assigning of constitutive models to finite elements that defines the internal stress strain behavior based on element material properties. So how these stresses will propagate, how the deformation would occur under different types of loads, when the material will yield is something internal to the structure, and that could be controlled by constitutive models. Then under external condition, we set the external factors like boundary conditions, loads, to complete the equation to be solved for the whole structure. And analysis is where the equations thus formed are solved. Then results are interpreted in various formats such as contours, graphs, tables, etc. So this brings us to the end of first chapter, and it's time for our first quiz. The quiz will have 3 questions and the duration is 5 minutes. So let me quickly share the quiz with you. So let's resume the session. So in chapter 2, we'll be talking about as how to set up analysis model. In this, we'll be going over the pre-processing part, that is what we have to do before hitting that button that runs the analysis in your programs. So we'll be covering the aspects of creating the geometry, meshing, assigning material properties, and finally the boundary conditions. So while creating the geometry, first of all, engineers have to decide whether which part of the entire topography they have to create the geometry for, to what extent they have to create the model for, and depending upon what type of structure that they are dealing with, they have to decide the dimension of analysis, whether a 2D model will be sufficient or a 3D model will be needed. So if you look at these two examples here, you will see that this is an embankment, or let's say a dam, and if I cut 3 uh, sections A, B, B, and C, I see that the sections are identical all throughout. So it really does not matter if I do a 2D analysis or a 3D analysis. So if I have to save time, and if I want to run something quick, I can quickly create a 2D model for this type of structure. So when your dimensions are not changing along the longer axis of the structure, then 2D analysis is sufficient. And if you look at this example, it's a tunnel with a connecting gallery. Section AA is different than section BB, and maybe it is similar to section C, but since I have to create a 3D model anyways, so it's always useful to create the entire structure with the connecting gallery in between. So actually we went over this 2D and 3D decision making in our previous sessions. So it is in this particular session, it will be largely a recap of different things that you have learned all over the sessions put together in creating a model. So once you have decided what type of model you would need, will it be 2D, 3D, or axisymmetric, then you can use different drawing tools which are either available in the software itself, or like I mentioned are available in the CAD software to generate the geometry. Whereas once you have generated the geometry in a different platform, then you can import the geometry into your analysis software. Some software have the capability to create the geometry itself within the analysis software, whereas some don't. So depending upon what kind of uh, platform you are working on, you can decide. But essentially the method remains the same. You have to create the geometry from scratch. So consider this example. There is a digital map which is available from different GIS software. So What engineers can do based on the area of interest, they can select a portion and extract that information into another software from where you can generate uh, the geometric data easily. So if you have these types of advanced tools, your modeling becomes much more easier, and since there are lesser number of software involved, so you take away that component of human error where you have to create in one, then bring it into another, and if you make any difference, let's say in unit systems, or let's say in different versions of the program, then sometimes uh, there are some minor errors which can be fatal for your projects. So again, depending upon the scale of your project and the importance of the project, you should pick the tool that works best for you. Then once the geometry is generated, let's move on to the discretization, and like I said, it is the most important step. So what we have to do, we have to divide the model by number of elements, where we have to create domains and geometry shapes, and then we have to decide as what size and type of elements will be needed. By size, I mean whether the element should be finer or coarser. As you can see here, this is the area of investigation where I expect greater stress concentration. So I'll have a finer mesh, whereas if I move away towards the boundary location where I don't have any stress concentration, I can have coarser mesh. So you have to pick the size of the element as fine or coarse. Then you have to choose the element type. By the type of element, I mean whether you have to use a triangular element or a rectangular element for your 2D analysis, or if for your 3D analysis, the triangular element is called as tetrahedron, and rectangular element is called hexahedron. Now, depending upon the choice of the element type, your results get affected too. So here's a tip for you. To check displacement results, triangle elements are good enough. So this is how a triangle element looks like. It is a 3D view, so it is basically a tetrahedron. If you use these type of element, you'll get good results for displacements. And majority of the time, geotechnical engineers are interested in the deformations and displacements, so they prefer using triangular elements. But let's say if your area of interest is to check stress results as well as displacements. So for that, it is always better to use a rectangular element over a triangular element. And a rectangular element in 3D is called a hexahedron, and it looks like this. So I repeat, triangular elements good for displacement, and hexahedrons or rectangular elements are good for displacements and stresses. Then let me go over the importance of the element size. So consider this given model. You can see the model is there, we have discretized it. This model has 4 elements, this is more, this is finer mesh, and this is the finest meshing. The load applied to all the 4 elements are identical, but when you look at the results, you'll get the stress contours something like this. So this is the result from the first, second, third, and fourth. And as you can see, from first to second, the stress contours have improved. From second to third, they have improved more. But if you see from third to fourth, the difference is not that significant, and it looks largely similar. So if you plot these results against the size, like the settlement or stresses, here we are discussing the settlement, with the mesh size, you can see that uh, finer the mesh, higher is the settlement, but after a certain mesh size, the results will not vary that much. So when you hit that point, this means that that is the optimal size you should use for your analysis. Because if you go with extremely fine meshing, it will be a very bulky model file and it will take a really long time to run. And at the end, the results will not improve significantly. So you would have invested more time for getting similar quality of results. So FEM results are highly dependent on the size of the element, and we need to decide proper size considering the efficiency as well as accuracy. And there should be a preliminary analysis before the detailed analysis. So whenever you are creating your model from scratch, always create an approximate model with very coarse mesh size, and then refine the mesh size slightly to get to a point where you will see that the deformations are not changing significantly, and that is your mesh size. Then let's move on to the second step, which is assigning the material parameters through constitutive material models. And while going over this process, let me quickly revise. So we have done the geometry, then we have created the meshes, and to this mesh we'll assign the constitutive model, and to this meshed model with constitutive material properties we'll add the load and boundary, and then we'll run the analysis to get stress and displacement. So right now I'll be talking in detail about the constitutive models. So if you look at this slide here, the first graph shows stress-strain relationship, and the stress-strain relationship varies for different type of materials. So you can see this is the hardening curve, this is the elastoplastic curve, this is the softening curve. And for this, let's say, embankment model, if you look at the stress path, then we have the soil strata here in triaxial compression. The soil strata here observes direct simple shear. The soil strata here experience triaxial extension. So basically the soil type might be similar or same throughout, still it experiences different types of forces and stresses throughout the stress path. So now based on what type of stresses they are subjected to, different curves are responsible for that behavior. So it is very important that you select the correct constitutive material model that correlates the stress strain graph with the stress paths that happen in the soil strata. And for this, the most commonly used constitutive material model is Moore-Coulomb. And here's a tip for you. So for shear failure, when you are checking for majority of your applications, you should be using Moore-Coulomb model, which is sufficient enough. And if you have to perform some kind of compaction and unloading behavior, then you should use Moore-Coulomb model. In addition to it, you should use equivalent linear stiffness component to simulate compaction and unloading behavior. But if you want to perform a non-linear compaction and shear failure analysis on the soil, let's say you are dealing with soil strata that are not very stable, that are poor soil with large volume changes that can happen, then that type of soil should be modeled using a constitutive material model like advanced models such as hardening model or modified Moore-Coulomb. So this is again a brief recap from what we have discussed or learned in the previous sessions as where to use what type of constitutive material model. And like I said, in this session we'll be focusing upon the main points that we have learned so far. So use Moore-Coulomb model in majority of your application until and unless you hit a soil strata type where you need to perform nonlinear compaction and soil shear together, and for that you should use modified Moore Coulomb, or advanced material models. Then let's move on to the boundary conditions. So boundary conditions can be applied in different forms. First of all is the constraints, where you can apply the fixed, hinge, or roller type of support. So let's say this is a 2D analysis that we are doing, and we want the soil to move in the vertical direction, so we have applied roller supports on the two edges, and we don't want the soil strata to move or go anywhere at the bottom, so we have applied a fixed support at the end. So you can have these kinds of boundary conditions applied as constraints. Then the boundary conditions could also be analysis related. So let's say if you are doing a hydraulic analysis, where such as simulation of seepage or groundwater flow, then you have to apply hydraulic conditions such as head, flux, or changing water level. So let's say this is a dam analysis, and you have to apply the seepage or simulate the transient flow. Then you have to apply the nodal heads and the water level on the either side of the dam to simulate this, and this is also accounted as a type of boundary. Then for simulating seismic analysis, you would have to apply dynamic boundaries such as damping, elastic, or transmitting springs. Then for slope stability analysis, you have to apply boundary as failure surfaces, which could be circular or polygonal. And boundary conditions can also be applied as structural components like plate or beam and releases, so depending upon your the behavior of your structural component. So this brings us to the end of chapter 2, and let's go over the points that we learned today. So first step in creating finite element model is to decide the dimension of analysis, whether 2D or 3D, based on the structure and the topography. So let's say your structure is symmetric all throughout, but the topography is changing drastically, then also you might need 3D analysis, because that will affect the loads that are coming onto the structure. 3D model is generally required when the cross section of your structure along with topography isn't uniform along the normal axis. And the software can read digital map and import information to generate geometry directly. So there are good software out there which can directly read complex geometry data from your digital maps and create geometry. And then while meshing or discretization, selection of element size, whether to use triangular or rectangular elements, and the size, whether to go for finer or coarser mesh, it greatly affects the analysis outcome. Use triangular elements for checking displacement only, whereas rectangular elements are good for stress as well as displacement results. Finer mesh gives better result but increases the analysis time. So therefore, based on the accuracy and efficiency that is required from your model, select the mesh size through preliminary analysis. I hope this point is clear. Then Moore Coulomb constitutive model is widely used to represent soil layer for common analysis involving shear failure. But for nonlinear compaction, advanced models like modified Moore Coulomb should be used. And the boundary conditions can be applied as constraints such as roller or fixed, analysis related such as hydraulic, dynamic, slope stability, and structural behavior related such as beam or plate and releases. So now it's time for second quiz. There will be 3 questions and the time duration will be 5 minutes. So in different types of analysis, there are stress deformation analysis, where you have to perform either a combination of static analysis with construction stage analysis. Then we have the problem of groundwater flow. For this, you have to perform a steady state and transient flow analysis. Then we have a problem of slope stability. So there, for finite element analysis, you should perform shear strength reduction analysis. Then for seismic problems, you can perform time history or response spectrum or 1D or 2D equivalent linear analysis. So these are the different types of analysis that are related to different geotechnical problems, and now I'll go over each one of these analysis in detail and talk about how different they are from each other, or what changes you have to make in your given model to do different type of analysis. So the basic steps remain the same. The first step, you create geometry and do the meshing through discretization. Then you apply the loading conditions, you define the boundary conditions, and then you apply construction stages. So this is something different that we have not covered in this session today. So what I'll do is talk about this little more. So construction stage is useful for simulation of how the actual site or the structure was constructed, and this includes the steps of excavation and installing different components. And why we are doing this is that we want to capture the stress history of the soil strata and the structural members. So if you can recall from the a couple of previous sessions when we talked about the importance of construction stage analysis, there you would have seen that how the stresses and deformation varies in contrast to the static analysis. So this type of analysis is useful for simulating embankments, excavations, or replacements, or hardening and softening analysis, and relaxation analysis. So let's see how the construction stage analysis is to be simulated. So first we have an initial condition where we set the displacement under self-weight as 0. So basically this is the stabilized soil strata with no excavation started. This is how the site will look like when you go there for your recognizing survey for the first time. Then you will start the excavation. So we take out the mesh components that are excavated. So now these stresses will be relieved here. There will be some sort of unloading because of removing of the earth. So you can see the stress distribution and deformation occurring. Then let's say we install the piles. Then we create the retaining wall, and then we apply the fill. After that we apply the first embankment, then second embankment, and then the third embankment. So this is a way to set up the construction stage analysis for an embankment project. And while we are doing this, we are also capturing the consolidation of what is occurring over the construction duration. So you can see the stresses that are developed and transmitted, or the stress history for different components of the structure. Then let's see how we have to simulate the groundwater flow. So the first step remains same. You create the geometry and do the meshing and discretization. You apply the constitutive material models in there. So basically your initial parameters are same. Then you define the boundary condition, which is essentially the main component of groundwater flow. And here if you see in your material property, you have to define the property for saturated and unsaturated flow based on different boundary conditions and permeability functions. And then you define as with what rate the head is changing. So you can say at 0 the value was 14, at 7 day it came down to 10, and then 30th day it was stabilized at 10. So you can apply these types of time varying functions as boundaries for seepage analysis. And then in order to capture this time effect, you can also simulate it during construction stages as mentioned in the previous analysis. So if let's say it was the same model that I showed you in the previous example, in that if I have to apply uh, groundwater flow in addition to the stress deformation analysis, only thing I need to do is under boundaries add the nodal head, flux or rapid drawdown with these functions. So that's all you have to do and you are ready with your groundwater flow analysis. Then slope stability. So the initial step remains same, mesh sets, loading remains same, and then the boundary conditions. Now here engineers have to define the failure surface, whether they are circular or polygonal. So you can see like this. So you essentially define the grade for LEM method, and you can see um, the various wedges that are created for analysis, and then you can simulate the construction stages. So again, going back to the same the first example, in the same example, if you have to perform a slope stability analysis, then in your boundary conditions, if you define as what will be the failure surfaces or define the analysis type as shear strength reduction, you can perform slope stability analysis. And in addition to the slope stability analysis, you can also add water level and consider seepage also. So with that you can also apply construction stages, and then it will become a coupled analysis or semi-coupled analysis. We covered semi-coupled and coupled analysis in the previous chapter, so I believe you are well aware of that analysis. And then let's talk about the seismic analysis, and this is a very special type of analysis, and engineers, being very honest to you, are somewhat hesitant in doing this type of analysis, and every time they want some easy way out so that they don't have to go through some cumbersome analysis and figure out the results. So let me tell you this: seismic analysis is a very simple, straightforward analysis, so there's nothing different about it. So what you can do is first create the mesh size, then you can create the loading conditions for time history, response spectrum, and dynamic loads. So you can get these kinds of ground acceleration graphs where you can apply different type of earthquake records to your structural strata, sorry, soil strata. And then you have to apply the boundary conditions. The boundary conditions could be as simple as some elastic spring, or be damping spring, transmitting boundary, or infinite boundary. So if you see this example, it is of let's say a retaining wall, and you want to perform seismic analysis to it. So all you need to do is grab the ground acceleration record, which is very easily available and generated by different either software tools, or there are several spreadsheets with response spectrum data in it. You can just copy paste and apply this type of ground acceleration by applying the springs. Now why engineers are hesitant in using this method is that it takes some amount of time or computation to generate these springs, and therefore engineers heavily rely upon numerical modeling tools to do this work for you. And it purely depends upon the numerical analysis capabilities of the software as to what extent it can help you in this process. There are some good software available where you can just select the boundaries and tell the program that I want to do a seismic analysis, so please generate the surface springs for ground. The program can automatically generate those springs for you. So I hope now it is clear that let's say for the same previous example that I showed you, if you would like to simulate a seismic analysis on it, you have your model and mesh in one place. You can apply the ground acceleration data to the entire structure, and apply boundary conditions at its outer periphery, and you are all set. So once you have got the basic ingredients in, which is the mesh and the internal condition, it's just a matter of playing with the external conditions, like how loading and boundary conditions are to be applied prior to analysis in order to get the desired results. So let's look at how to obtain the results. So different components of the model are important, and they are used for looking at different types of results. So if you are interested in looking at displacement, you should look at the nodes and their value in tabular format or graphical format or contour plot, something like this. Then if you want to look at the stresses, then you have to look at the nodal data. If you are talking about the solid or the ground, or if you want to look at the stresses in the elements, then you can directly look at the element results also, something like this. So this is a 2D retaining wall here. You can either click on different nodes and get the stress values, or you can see the contour plot in the plate elements that are used here, and get the stress results. Then engineers are also interested in structural results that can be used for designing of the components. So for this, you can look at the element results, like the bending moment diagrams of the pile members. So you can see this is the bending moment diagram along the pile length. So you can extract these types of results. So again, for displacement, you should look for the node results. For stresses, you should look at nodes or elements, and for structural results, you should look at the elements. And then these results can be extracted in different platforms. It could be either contour plot, it could be the diagrams, it could be tables or text, whichever is comfortable or required for your work. So this brings us to the end of chapter 3, and let's go over the key points we learned today. So the analysis type depends upon the objective. For stress deformation analysis, construction state definition is mandatory to capture the stress history. For simulating groundwater flow, special boundary conditions such as nodal head, flux, rapid drawdown are needed to be defined in addition to construction stages. And the failure surfaces, could be circular or polynomial, are defined as boundary conditions for slope stability analysis. And for seismic analysis, you require special loading conditions like ground acceleration response spectrums and or dynamic loads with special boundary conditions such as elastic or damping springs. And different components of the model must be looked for different results. So displacement results can be obtained from nodes, stress can be obtained from nodes or elements, and structural results can be obtained from elements. And the results can be obtained in different formats. So now it's time for our third quiz. The duration would be 5 minutes, and there will be 3 questions. So now we'll move into the the final part of this session, which is the case study, and here we'll be talking about the modeling process. So you can see that this is a 2D model of a bridge embankment, and we have different types of soil strata here. And we have the embankment with the pile members. This is the abutment, embankment 1, embankment 2, then clay layer, weathered rock, soft rock, and we'll be going over as what are the main steps that what we have learned today are applied for this type of structure. And in this particular example, I'll be taking the most complicated type of analysis that engineers think, that is seismic analysis, and I'll show you how simple it could be. So we'll be starting with the modeling and the meshing considerations that are to be made, then the internal conditions that are defined. So we'll be reviewing what constitutive material models have been used for different soil types. Then we'll be going over the external condition where we have to apply the boundary and loads, and this part depends upon the analysis. So if we are doing seismic analysis, we'll be applying the boundary conditions and loads as per such as time history loads and springs like damping springs, and then we'll run over the analysis and extract the results. So this is a software interface. The software, you can see that, and on your screen you can see this is a 2D layout of that model. Now depending upon the software capabilities, you can generate the geometry, as you can see at the top, like creating lines and polylines and surface to get this kind of outline. If you have this kind of outline already in your, let's say, CAD drawings, you can directly read it by various import features, such as you can see here. Once you have imported this CAD drawing, now the next step is that you create surfaces or you mesh the strata. So what we have done here is we have already applied mesh to this strata. So here, based on different type of layers and the dimensions, we have applied meshes, and our prime interest in this analysis is displacement. So you can see we have used triangular elements. So every element has 3 nodes, as you can see throughout. And since this is a very simple example, they are not extreme, I should say, stress concentration points. So therefore, uh, we have applied a uniform mesh size all throughout, as you can see. But in closely spaced locations such as this, you can see the meshes are slightly denser than the other locations. And this is a 2D model. Now the reason we decided to go for a 2D model here is that the element or the section was not changing along the normal axis. So if I go click on one of the buttons here, you can see that along the normal axis, this will be the normal axis, and we have just cut one section and we are analyzing it. Now if I have to generate a 3D model out of it, I can just select everything and extrude it along the normal axis to create a 3D model out of it. So once you have generated the meshes and everything, then let's review the material properties of the constitutive models that have been used, that can be found in the model, and you can see the properties here. So we have embankment, clay, weathered rock, soft rock, embedment, and steel pipe pile. So for embankments, you can see we have used the constitutive material model as Moore Coulomb. Now if you are dealing with a soil strata which doesn't obey the Moore Coulomb and you would like to use a different type of constitutive material model, you can choose from different options that are available right here. For clay, we have used different latency angle here. You can also control the seepage parameters. So now if in the same model, if I want to do, let's say, groundwater flow, I can control the seepage parameter. I can consider unsaturated property. I can define different types of functions like I showed you in the presentation before. And then for weather rock, soft rock, abutments, For abutment we are using concrete material, so we are using an elastic type of constitutive material model. And then we have steel pipe for piles, so we have used steel material. And for structural members, as you know, in geotechnical problems we assume them to be within the elastic range and they are not yielded. So we usually assume elastic type of material behavior for structural components such as concrete and steel. Unless it is really needed, then we do a non-linear type of analysis. So once we have defined the internal behavior for different types of soil layers, then we go ahead and define the boundary. Now, like I said, this is a seismic analysis, so we have to define different types of boundary at the periphery. So for this we have to define springs, and definition of springs could be done under elements, and you can see there are different ways of defining springs. It could be a surface spring, it could be create ground surface springs. So if you have a software similar to MIDAS GTS, where you can just select that you based on the subgrade reaction and elastic modulus of elasticity coefficient, the software can automatically generate the mesh the springs for different mesh sets boundaries. So it will automatically identify what are the periphery nodes and create springs there based on the subgrade reaction that you have selected. Now if you don't have this kind of tool, then what you can do is you can generate normal springs. So you can go to elements and generate springs with different properties and interfaces all along the periphery. So once you have applied these springs as the boundary, you can see it under a given mesh set. So if I click here, you can see damping spring mesh, weathered, clay, soft rock springs, and dynamic springs here for different layers. Now let's say we would like to do a construction stage analysis in the same with the same geometry. Okay, so what you can do is just go into model and define construction stages, and here you can simply select the mesh sets that you would like to activate in a particular stage, and then take out the mesh set that you would like to deactivate, and then set up a construction stage. So once you have generated the basic geometry, it's purely up to you to decide what type of analysis you would like to perform depending upon what you would like to achieve. So you need not change anything in the model once it is generated. All you need to do is just change the external factors like boundary conditions and loadings to cause different variations. So if you would like to do a slope stability analysis, here you can define the failure surface, or you can set up analysis type as SRM, which is shear strength reduction method, and the program will run that type of analysis. So here we have defined the boundary conditions, and then let's go over the loads. So under loads, you can apply self-weight, force, moments, prescribed displacement, pressure load, line beam, element beam load, temperature load, pre-stress load, or response spectrum or time history loads. So here we have defined time history load sets, as you can see here, where you can define as what type of analysis you'd like to perform: linear, direct integration, start and end time. The damping should be mass proportional and stiffness proportional, and the frequency calculations based on eigenvalue analysis. So one thing you should always remember while performing any kind of seismic analysis, you should always do an eigenvalue analysis as well. And eigenvalue analysis gives you how the entire system would oscillate at different, and what will be the period of those oscillations, and based on that then time history load can be applied onto the structure. So once you have defined the, uh, the the time history load set, then you can define the forcing function, which is something like this. So here this is the ground acceleration data that you can bring in from different sources. You can either copy paste from spreadsheets, you can import from some other files, or you can select different type of earthquake records and directly generate from there. So again, this is more of a software capability limitation. So based on what tool you are using, or irrespective of what tool you are using, you have to bring in ground acceleration data from some source. Now once you have brought in this ground acceleration data, all you need to do is just set up the analysis type. So if you go to the analysis tab, you can see we are performing eigenvalue analysis. We are performing time history analysis for 3 different types of time history functions. And then you can compare the results based on 3 different types of ground accelerations here. So if I just click here and say modify, you can see under the analysis type all different analyses are available. So you can choose, we want to perform time history linear analysis, response spectrum analysis, seepage analysis, slope stability analysis, consolidation analysis. So you can select what analysis type you would like to perform after setting the basic parameters, which is step number 4. Once you have set up the analysis type, all you need to do is just go to the analysis and hit the solve button, where you can select what analysis you would like to perform. And if there are multiple analyses but you just want to look at, let's say in the same model I am performing a slope stability analysis, seepage analysis, and dynamic or seismic analysis, and I am satisfied with the results of seepage and slope stability, and I would like to just rerun the time history analysis, then I can just select the analysis that I would like to rerun. But once again, this is a software limitation, so based on what platform you're using, or irrespective of what software you're using, you must perform the analysis after setting up the analysis controls. So once the analysis is done, then it's time to look at the results. So I have analyzed this model, and you can see there are different tabs. So model contain all the pre-processing data, and the analysis tab consider all the analysis data. And now we are in the post-processing, where we can see different types of results. So let's say I want to look at the eigenvalue mode shapes, and if I click here and just scroll through this button, you can see the results in contour plot. And let me just scale this structure a little bit so that you can see it more clearly. So if I just move across different mode shapes, as you can see, 7th, then 8th, 9th, 10th, 11th, 12th. So we have considered different mode shapes, and their time and the frequency are also mentioned here. And similarly, you can change and see the results for time history functions. And right now we are looking at the displacement along vertical axis. I can change the results, so you can see the results in dxyz, and again you can just click on different lengths of function times, so you can see the results. Also you can click on these type of results here and look at the reaction displacements at different time intervals. You can look at velocities, acceleration. So these are different ways of looking at the contour plots. And if I'm interested in looking at the uh, element results, then I can just look at the 1D forces, such as the bending moment in the pile members alone. So you can see the bending moment plot. So this is how you see the structural forces. And if you want to see the results for stresses, you can look at the stresses along different angles, or sorry, different axes. And you can see the same result in a tabular format. So you can go to tables, and the program generates a tabular output for you. So for each and every element, it has its coordinate as well as the value for all 6 forces or stresses. And if you are looking at the time history results, so I showed you how to check the results of in contour plots, how to see the results for the structural members, how to generate the tables. Now let's see how to generate the graphs. So under results, we have a special type of result called time history graph for time functions. So you can select a function here and then just hit apply. So this is basically the lateral displacement of one of the nodes onto the structure, and you can see under the time history or the time history record function that you applied, or the ground acceleration that you applied, how the structure is oscillating. So there are different ways to look at different types of results. Contour plot will not be sufficient if I want to look at the oscillations like this, but if I want to see how the stresses or the displacement occurs for the entire structure, then this graph wouldn't be sufficient, and I have to look at uh, the contour plots. And at the same time, if I just want to see some particular results, I can look and refer to the um, tabular format. So again, depending upon what kind of results you are looking for and what is your intent of analysis, it is wise to choose the appropriate type of result output. The results can also be generated in a text format, again, so that can be used for report generations. So that was all that I wish to cover today in the presentation. I hope you got a good idea about the you got a good idea about how to do numerical analysis, what are the main uh, steps involved in numerical analysis, and how you put together a model for analysis, and where uh, you need finite element analysis. So this concludes the session for the day, and this was the last session of our first course. So I hope you enjoyed and you learned something. Here are my contact details. Please feel free to contact me for any kind of question that you may have, and we'll be more than happy to address them. So once again, I thank you all for joining in. This is Arun Sharma signing off from MIDASoft. Have a great day ahead. Thank you. Bye-bye.